Titan, a terrifying world where oceans are made of gasoline. Imagine standing on a shore. The waves crash, the tides roll in and out, the liquid around you stretches to the horizon in every direction. Now imagine that if you struck a single match, the entire ocean would explode into a fireball visible from space. This is not a nightmare. This is not science fiction. This is Tuesday on Titan, and it is happening right now, 886 million miles away as you read these words. Titan is Saturn's largest moon and the second largest moon in the entire solar system, larger even than the planet Mercury. It sits so far from the sun that sunlight arrives 100 times weaker than it does on Earth. The surface temperature is minus 179 degrees Celsius. And yet, against every expectation, against every rule planetary scientists thought they understood, Titan has weather. It has seasons. It has rivers, coastlines, and vast open seas. It has an atmosphere thicker than Earth's own. Between Titan's oceans and the ones on Earth is that Titan's oceans are made of liquid methane and ethane, hydrocarbons, the same chemical family as gasoline, natural gas, and petroleum. Before Titan, we thought we understood what a world needed in order to matter. It needed to be warm. It needed liquid water. It needed to sit close enough to a star to feel its heat. Earth gave us the template, and for centuries we measured every world against it. Titan did not just bend that template. It snapped it in half and handed the pieces back to us with the quiet confidence of a world that has been doing extraordinary things for 4.5 billion years without asking our permission. The Cassini spacecraft arrived at Saturn in 2004 and began stripping away Titan's mysteries one revelation at a time. Its radar instruments punched through the thick orange haze that had hidden Titan's surface from Voyager 1 back in 1980, and what they revealed sent shockwaves through the planetary science community. Lakes, river delta systems, drainage channels carved through terrain made of water ice so cold it behaves like rock. The largest of Titan's seas, Kraken Mare, covers an area larger than all of North America's Great Lakes combined. It is filled not with water, but with liquid methane, sitting calmly on a frozen world at the edge of the solar system, lapping at shores made of ice pebbles and organic sediment under a brownish-orange sky. The rain on Titan falls, liquid methane. It carves rivers through ice rock mountains. It pools into dark seas that reflect the distant glow of Saturn, hanging enormous in the sky, 8 times larger than our full moon appears from Earth, its rings casting long shadows across its face. Titan is running a complete hydrological cycle, the same kind of cycle that fills our rivers and carves our canyons and sustains all life on Earth, except the working fluid is not water. It is something we use to fill our cars. But here, where the story of Titan stops being merely spectacular and becomes something closer to earth-shattering. In Titan's upper atmosphere, the faint ultraviolet radiation from the distant sun breaks apart methane and nitrogen molecules and reassembles them into complex organic chemicals called tholins. These molecules rain down onto Titan's surface continuously and have been doing so for billions of years. Scientists estimate that the total organic carbon sitting on Titan's surface exceeds the entire known oil and gas reserves of Earth by hundreds of times. Titan is not just a world with some liquid on it. It is a world saturated with the raw chemical ingredients that on Earth eventually produce life. And that is the question that haunts every scientist who has spent serious time with Titan's data. Could something be alive there? Not life as we know it, not something that needs liquid water and breathes oxygen, but something that uses liquid methane as its solvent. Hydrogen metabolizes acetylene as an energy source and produces methane as waste. This hypothesis was published in the peer-reviewed journal Icarus in 2005 by astrobiologists Chris McKay and Heather Smith. It was not speculation. It was a scientific hypothesis with testable predictions. The prediction said that if methane-based life existed on Titan, hydrogen near the surface should be depleted and atmospheric acetylene should be consumed. When Cassini's data was analyzed carefully, scientists found exactly those anomalies. This does not prove life, but it is the kind of signal that responsible scientists file under words worth investigating further. Investigating further is precisely what humanity is now committed to doing. In 2019, NASA announced the Dragonfly mission, a rotorcraft lander the size of a large car that will fly through Titan's thick atmosphere in the 2030s, landing at multiple sites, collecting samples, analyzing chemistry, and searching for the molecular signatures of life. It will fly to the Selk impact crater, where an ancient meteor strike melted Titan's ice crust and mixed it with surface organics, briefly creating the same water-organic environment many scientists believe sparked life on early Earth. Dragonfly will be the most ambitious planetary exploration mission ever attempted, and what it finds will be among the most consequential discoveries in the history of science. Titan is a time machine pointed at our own origins. 4 billion years ago, Earth's atmosphere was thick with nitrogen, methane, and complex organics, the same chemistry Titan wears today. The experiment Earth was running then eventually produced DNA, cells, organisms, ecosystems, and eventually a species curious enough to point telescopes at distant moons and wonder what was happening there. Titan has been running its own version of that same experiment at -179 degrees in methane instead of water for exactly as long as Earth has been running its. We do not yet know what Titan's experiment has produced, but we are going to find out. This is the deepest lesson of Titan. The universe does not arrange its phenomena to confirm our prior beliefs. It does not require warmth or sunlight or liquid water or any of the conditions we once insisted were mandatory for a world to be interesting. It requires only chemistry, energy, time, and the right conditions for molecules to meet, react, and iterate. Titan has all of those things in extraordinary abundance. And it has been working quietly, patiently, brilliantly while we were busy assuming it was just a cold orange dot orbiting a gas giant at the edge of everything familiar. The oceans of Titan are real. They are made of something that burns, and somewhere in their dark, methane-cold depths, the universe may be answering the oldest question we have ever asked. We are almost there, and we are finally ready to listen.